Section 3.7, the chain rule. This is a fun one as well. Derivatives are just fun. Okay, so before I begin, I want to emphasize one thing, specifically with trig functions. If I have sine squared of x versus sine of x squared, hopefully in your trig course, you've noticed or someone emphasized the difference, right? Here, we're taking the value of sine, and once we find that value at sine, then we square, right? Versus here, first we square that value, and then we go ahead and apply sine. So sine of whatever has been squared. So it's kind of like an order of operation issue. This can be something that can be kind of misleading in this section. And if you're ever confused, if you're ever unsure, think of it this way. This means sine of x squared, and this means sine of x squared. If it's helpful, it would be worth your time to rewrite this way to avoid a silly error. Okay, let's continue with the section. We start off with theorem 3.12 from the chain rule. The theorem reads, suppose y is equal to f of u is differentiable at u equals g of x and u equals g of x is differentiable at x. The composite function y equals f of g of x is differentiable at x, and its derivative can be expressed in two equivalent ways. dy dx is equal to dy du times du dx, and d dx of f of g of x is equal to f prime of g of x times g prime of x. Using the chain rule. Assume the differentiable function y equals f of g of x is given. 1. Identify an outer function f and an inner function g and let u equal g. 2. Replace g of x with u to express y in terms of u. So y equals f of g of x, which implies y equals f of u. 3. Calculate the product dy du times du dx and replace u with g in dy du to obtain dy dx. When I was in your position and I tried to follow these instructions, they were very misleading to me and I would often do silly mistakes. So I wouldn't do that procedure. What really helped me was when I went to tutoring and the tutor told me that the best way he can describe it is in his words, or in just general layman's terms, it is the derivative of the outside times the derivative of the inside. Okay, so in this for example, I'll try to highlight the procedure given, and then I'll show you how you use that saying, the derivative of the outside times the derivative of the inside. And I feel like that's a bit more easier, more realistic procedure to follow. Okay, so what we're working with, so your example says, for each of the following composite functions, find the inner function gu gx and the outer function gy, y equals f of u. Afterwards, apply the chain rule to find dy dx. So the idea is that you have composition of functions. So our function here is that we have this inside function, y equals u of 3 over 2. And then we have the outside function, u equals, the inside, 5x plus 4. So we have two functions where we're applying composition, and that's the idea of this. So first we want to identify our u. in our function. So we have our u here. 2, replace gx with u to express y in terms of u. We have this done here. That's your step 2. Okay, now your step 3. You want to calculate dy du times du dx. Okay, so for our first one, we're taking our function y and we're taking the derivative of u. Okay, so we take the derivative of u, we have 3 over 2 times u, and we have 3 over 2 minus 1, which is 2 over 2. So we get 3 over 2 times 1 over 2, right? And we're going to multiply the derivative of u in terms of x. This is our u in terms of x. So the derivative would just be a 5 because the derivative of a constant is 0. So derivative of 4 is 0. So there we have our derivative. Now we multiply. So our answer would be 5 times 3 would be 15 over 2 u to the 1/2. We don't like that exponent of 1/2. So we'll write 5 over 2 square root of u. So we have 5 square root of u over 2. So there we have it. That is chain rule. I don't like chain rule in that definition. So let's do it differently. So let's go ahead and take the derivative of the outside and the derivative of the inside. So for our problem, we have 5x plus 4 over 3 over 2. Okay, well, let's take the derivative of the outside. The outside is that exponent. So I have 3 over 2. We write the same thing. And then we do power rule, so we subtract 1. We see that we get 1/2. Now I take the derivative of the inside, which is just that 5. The derivative of 5x is 5. And we get the same result, but you kind of do part of it in your head. So your answer is 15 over 2, 5x plus 4. You see, I even forgot to plug it back in what u is in the other problem. 1/2. So we have 15 times the square root of 5x plus 4 over 2. That is our answer. And you see we have a mistake here. That was a u, and we need to replace u back. So I have 5 square root, and we said u was 5x plus 4 all over 2. That u substitution with derivatives and chain rule, it's not what I practiced, so it's really not what I do. I do follow that idea of derivative of the outside times derivative of the inside. Okay, let's do sine cubed of x. So if it's helpful to avoid doing a silly mistake, you can rewrite this. This is really y equals sine of x cubed. Okay, well, let's take derivative of the parentheses and the exponent. So that we get 3, same thing in the parentheses, and then 3 minus 1, we get 2. Now I take the derivative of the inside. Derivative of sine, we learned from our last section, is cosine. And there we have it. That is our answer. Our answer is 3 sine squared x cosine x. Now, as I'm looking at my notes, so to record a lecture for you guys, I do prep my notes, I do reread the section, and I try to be as careful as I can. And I'm seeing in my notes, I have mistakes when I follow that procedure of chain rule. So my best suggestion is to follow that. Take derivative of the outside, multiply it by the derivative of the inside. Okay, here we have sine of x cubed. So our outside would be our sine. Let's take derivative of our outside. Derivative of sine is cosine. So I have cosine x cubed. Now I'll take derivative of the inside. Derivative of 3x is 3x squared by using our power rule. So that is our answer. We can write the 3x first so that we have 3x squared cosine of x cubed. D. Y equals 6x cubed plus 3x plus 1 to an exponent of 10. So let's take the derivative of the outside. Let's take derivative of the exponent of parentheses, exponent 10. So let's bring the 10 forward. We have the same thing in the parentheses, and 10 minus 1 is 9. So just writing the same thing in the parentheses. Okay, now let's take the derivative of what's in our parentheses. Our derivative of that would be 6 times 3 is 18, x squared. We have 3x plus 3, no x, and derivative of 1 is 0. So that is that. Okay, now I can factor out a 3 from these so that I have 3, and I'm just factoring. I'm just trying to remove as many constants as I can to the front. So we have 6x squared plus 1. That way I can multiply these guys. So I'm left with 30, 6x cubed plus 3x plus 1 to 9th power times 6x squared plus 1. And kind of like an unwritten rule in any algebra course, you always want to factor fully. So if there's a constant to factor, you want to make sure you do that. How are you doing so far? Now, I also remember when I first learned chain rule many years ago, it was something that I struggled with, but only through the effort of doing my homework and asking questions did it make sense. So this is tricky, but once you get it, it's one of those things that you enjoy. You're like, okay, I got this, I can move forward. I get it. Okay, we have problem E. Y equals the square root of 5x squared plus 1. So whenever you have a rational exponent, you can write it as a root, a radical, with some index and some exponent. But you can also rewrite it as a rational exponent. So we can rewrite this as 5x squared plus 1 raised to the 1/2 power. That makes it a lot easier to identify your outer and your inner, right? So let's take the derivative of the outer. So we bring forward that 1/2, and we have 1/2 minus 1. You get negative 1/2. Okay, let's take derivative of the inside. So we get 5 times 2 is 10x. 2 minus 1 is just 1. Derivative of 1 is 0. There we have it. Okay, so let's clean this up. 1/2 times 10 is 5. So I have 5x times 5x squared plus 1 raised to negative 1/2. And in math, we do not like to have negative exponents. So let's go ahead and move it forward. Move it down. We have 5x, and in the bottom, I have that quantity with the negative exponent. 5x squared plus 1 to the 1/2 power. And for our answer, we do not want to keep that rational exponent. We write it using a radical. So we have 5x divided by the square root of 5x squared plus 1. There we have it. Okay, F. Now, all the process and the processes that you learned for taking derivatives still apply. So recall your product rule, which says if you have two x's being multiplied or two arguments of x's being multiplied, you consider one to be f and one to be g. So it's f prime times g plus f times g prime. We also have the quotient rule, which is f prime of g minus f g prime divided by g squared. Those are those special derivatives, right? When I have f times g and when I have f divided by g. That's how you find those derivatives. And I'm just recalling them because you will see them. Okay, let's take a look at this example f. So I want to apply chain rule. Now, if we apply chain rule, I want to take the derivative of the outside. So I bring that 3 forward. Same thing in the parentheses, 3 minus 2, or 3 minus 1 is 2. We have 5t squared divided by 3t squared plus 2. But now I'm left to take the derivative. I haven't taken the derivative of the inside, which is 5t squared divided by 3t squared plus 2. So to take the derivative, to find that prime, I have to use my quotient rule, right? Where this is f and this is g, our derivative can be made up of. The derivative of f is 10t, and then our g is 3t squared plus 2, minus our f is 5t squared times the derivative of your g, which is just 6t. That 2 is 0, so we don't need to write that down, divided by 3t squared plus 2 squared. And that's just derivative of our inner. We still have to bring down our outer. Okay, so let's rewrite this. We have 5t squared divided by 3t squared plus 2 squared times, we can multiply these in, distribute that 10. So we have 10t times 3t squared gives us 30t cubed. 10t times 2 plus 20t minus 5t times 16. That gives us 30t cubed divided by 3t squared plus 2 squared. Okay, now we see that our t cubes add to make 0. And we are left with this rational function. And we can actually apply the radical to the numerator and to the denominator, so that we have 3 times 5 times 5 is 25, t squared is 4, t to the 4th power, 3 squared is 9, t to the 4th power. Oh, that's not the denominator. You need to actually do the binomial, right? So I'll just write it as something squared. So we have 3t plus 2 squared. Okay, so we have 20t, and we have 3t squared plus 2 squared. Let's go ahead and clean it up. So we just multiply across. This one's not so bad. So I have 3 times 25 is 75, and 75 times 20, 1500. So I have 1500 t to the 5th power, and we have the same base, so we just add the exponents. 3t squared plus 2 to the 4th power. That is our answer. All right, we see that the calculus didn't take us so long, but the algebra is what took us to finish. Theorem 3.13, the chain rule for powers. If g is differentiable for all of x in its domain and p is a real number, then d dx of g gx p is equal to p times g of x of p minus 1 times g prime of x. All right, example 5. Chain rule for powers. Find d dx of, or the derivative of, tangent x plus 10 to the 21st power. So we still do the same thing we've done in the past. It's not anything different if you think of it as the derivative of the outside times the derivative of the inside. So the derivative of the outside, let me rewrite it. Tangent of x plus 10 raised to the 21st power. We bring it down, 21, and then we do power rule, 21 minus 1 is 20. We have the same thing in the parentheses. Now I take the derivative of the inside. Derivative of tangent is secant squared, and we learned that from our last section. And derivative of 10 is 0, so we don't need to write that 0. And that's it. That's your derivative. Okay, one more example in combining rules. So we see that here we have product rule and chain rule all nested together. We have product rule because we have two arguments of x being multiplied together, right? And we have chain rule because we have that radical. Okay, so let me rewrite it. We have x squared times, well, maybe I shouldn't write too many parentheses. I don't want parentheses overload. Times x squared plus 1 raised to the 1/2 power. Okay, so we see that to proceed, I have to use product rule. So to remind you, product rule is the derivative of two functions being multiplied by each other is f prime of g times g plus f times g prime. Okay, so we consider this to be f and g. Let's take the derivative. So the derivative of f is 2x. This one is 2x. And then times our g, which is just x squared plus 1 raised to the 1/2 power. Plus, my first one, your f, is going to be x squared. And then derivative of your g is, well, we have to do chain rule to take derivative of that second portion. So we do 1/2 times x squared plus 1 raised to the 1/2 power. And the derivative of the inside is 2x, since the derivative of 1 is 0. Okay, now it's just, that's a calculus. The next is a lot of algebra. Let's try to clean up as much as we can. So for this first term, I can't distribute in that 2x, so it just stays as is. 2x times x squared plus 1 raised to the 1/2 power. All right, plus, well, I can multiply those two monomials so that we get 2x cubed. Ooh, I can multiply in the 2, so it's just 1 now. 1x cubed, or just x cubed. And we have x squared plus 1 raised to the 1/2 power. And for the sake of factoring, we can factor out their common factor. No, we can't because I made a mistake. I made a mistake here. So when we subtract 1/2 minus 1, we get negative 1/2. So this is supposed to be a negative 1/2. So we can't factor anything. What we can't do is write that negative exponent down. So we have 2x times the square root of x squared plus 1 plus x cubed with the square root of x squared plus 1. And there we have it. This was chain rule. Now again, it could be tricky. If you do, just go on to your homework and try to practice it. Maybe it'll make more sense. I highly suggest that you just think of it as the derivative of the outside times the derivative of the inside. That's the best way to go about it, and a lot less writing. Use substitution is very helpful, but it's more helpful towards the end of the course when we do like integration using substitution. That's where you'll see it be super helpful. All right, that's it for section 3.7, the chain rule. Thank you.